We're saying for Newton's third law, for every force, there is
Mhm.
a force that is equal in magnitude, but opposite in direction. Well, if you're saying this makes sense, let me ask you then, if we have, for example, a box, and you've got a person who's pushing it. So let's say the person pushes the box with 100 newtons of force, right?
Uh-huh.
Now, according to this law, there must be a force that's equal in magnitude, but opposite in direction. So there must be a force that's 100 newtons to the left, right?
Yes.
So if this box has 100 newtons to the right from the person, and there's 100 newtons to the left, does that mean the net force is 0?
Uh,
Right, 100 newtons to the right, 100 newtons to the left. Does that mean the net force is 0?
yes.
So does that mean the box won't move?
Yes.
But then how can any box move, right? Because, I mean, it doesn't matter how hard I push the box, right?
Mm-hmm.
I push to the right by 1,000. There's going to be an opposite force of 1,000. And they'll cancel each other out, and then there's no force, right?
Yes.
So I think, I mean, so it means no matter how hard I push the box will not move. And that will apply to everything, yes?
Uh-huh.
How does that make sense? I mean, we know we can push boxes and they do move.
Mm-hmm.
So does this law seem right?
No.
So what's wrong with this idea?
Uh,
Okay, so you've had a little bit of time to think about it. Have you figured out the problem here yet? Or is it still very, very confusing?
because of the weight.
No, it's got nothing to do with the weight.
So I'm still confusing.
Yep. So this is a very confusing law to many students because they don't really understand it very well, okay? But let me ignore Newton's third law for the moment. Let us completely ignore Newton's third law and let's do something else for a little bit. And then let's come back to this, all right?
Okay.
So let me just ignore physics. Let's think of something else. So let's say you've got two people. You've got Jack and you have Jill, okay? And they're friends.
Okay.
All right. Now, Jack and Jill are, both going to school, and Jill doesn't have money to buy lunch. And because they're friends, Jack happily gives $10 to Jill to buy lunch.
Mm-hmm.
To buy lunch kind of thing. So the point is, Jack gives $10 to Jill, yes?
Yes.
Now, if we were to say, if we say Jill, did Jill give or get money from Jack?
I get money from Jack.
So Jill would have, received, basically got. And how much would she have gotten?
$10.
Right. All right. So you understand that, one person gives some amount to Jill and that this person must have received some amount from this person, right? This is really the same thing, but two different ways to think about it, yes?
Mm-hmm.
One person must give, one person must give. And if one person gives, what must the other person do?
Receive.
They must get, obviously. Yeah? That's just the way it works. One gives, one gets. All right. If one gives $10, how much does the other one receive?
$10.
Right. Can these amounts ever be different?
No.
Basically, no. I mean, if we're ignoring, things like money getting lost or stuff like that, which, in our simple example here, just there's no bank fees or anything weird like that, the numbers must equal. Agree?
Yes.
You can't give $10 and they got 5. That doesn't make sense. You can't give and they also give. That doesn't make sense either.
Yeah.
So it's very simple. If Jack gives $10 to Jill, then two ways to think about it. Jack gave, Jill received, right?
Mm-hmm.
And that means Jack would have lost $10, but that means Jill would have gained $10.
Yes.
And so no matter how much Jack lost, Jill must have got the same amount, yes?
Mhm.
All right. So that's one thing that's very, very, that many students get wrong. Firstly, when we say, back to Newton's third law, for every force, there is a force that is equal in magnitude and opposite in direction. This is true. This statement is true.
Okay.
But many students think incorrectly that, okay, I push the box to the right by 100. According to this law, there is a force to the left by 100, which is true, by the way, but we'll talk about that in a moment. And then they go, that's cancels out to, this is where it starts getting wrong. This starts where it gets wrong, all right?
Mhm.
There's a force 100 newtons to the right.
Yes.
There is a force 100 newtons to the left,
Mhm.
but this force is not on the box. That force is not on the box.
Yes.
So it might be easier to think about it more specifically and think about the fact that you've got, think of a giver and a receiver, right? So you've got, the giver, if you like, gives an amount.
Yeah.
And with a direction to the receiver. So for a force, there's always a sort of a giver and a receiver, basically. So for example, I might say that the person pushes the box to the right with 100 newtons of force. So the person is the giver here. The person pushes to the right, pushes to the right 100 newtons on the box. Does that make sense?
Yes.
Now that is a very, very simple statement of a force. Now, based on Newton's third law, there is a force that is equal in magnitude. So this opposite force I'm going to do in blue. The opposite force will be 100 newtons because it's equal in magnitude.
Mhm.
And it will be opposite in direction. So the direction is to the right. So this will be to the left. So there will be such a force, all right?
Yeah.
Except no one ever said this is on the box. In fact, it is never on the box.
Ah.
The person and receiver will swap. So basically this is the box giving the person 100 newtons of force to the left now. So now think about it this way, right? The harder you push a box, does the box push harder against you? Like, does it feel harder to push the box harder?
Mhm.
It does. So these are your opposite forces. Does that make sense?
Yes.
But importantly, these forces, while they are equal in magnitude and opposite in direction, one is acting on the box, one is acting on the person. So the box does not have two 100 Newton forces cancel each other out because only one of the forces act on the box.
Yes.
Does that make sense? So
Yeah.
let's now say, for example, if you are standing on the ground,
Mhm.
is there a force pulling you down?
Yes.
All right, so let's say you've got someone, let's say they're 70 kilograms, and let's make the numbers easy. So there's the force of gravity pulling you down, right, with 700 newtons. So this is the gravitational force, yeah? So gravity is pulling a person down. Yeah?
Yes.
Oops. The receiver is the person. The person is being received. All right, what's giving the force?
Gravity.
Yeah, but gravity has to come from somewhere.
Uh.
Gravity has to come from somewhere.
Earth.
Yeah, Earth. So if you're on Earth, the right thing would be to say that Earth is pulling the person down with 700 newtons of force. Right? So this is a curious example here. So let's imagine that you've got the person standing on the ground. All right. And they've got, 700 newtons of force acting on them downward. All right. If you've got 700 newtons of force acting downward, then, well, what's the opposite force to this?
700 Newton upward.
It would be 700 newtons upward, but what would that be, so you do have a 700 newton force upward, but what's that acting on? From what? What is that force?
Acting on Earth.
Yeah, you're right, 100%. So lots of people say it's the normal force, which is not, all right? So the opposite to this, you're right. It would be 700 newtons pulling up on Earth from you. So if Earth is pulling you down with 700 newtons, the opposite force to that force is you pulling up on the Earth with 700 newtons. You're 100% right there.
Yes.
All right. Lots of people say it's the normal force. The normal force is not the opposite force to the gravitational force pulling you down. Now, there is a normal force on you, but that's not the opposite force to the gravity pulling you down.
Okay.
There's gravity pulling you down, and the opposite force is your gravity pulling it up. Right?
Yes.
Having said that, if we're looking at the forces, so, this is the force on Earth by you, and this is the force, on you by Earth. Having said that, we haven't talked too much about the normal force, and we will do that as time goes on, hopefully today. But if we're looking at, say, a weight of an object, we say that there's a normal force also acting on that object, right?
Yes.
So think about this. The normal force, so let's say we've got a box. What's giving the box the normal force? You've got a box. What's giving the box the normal force? And let's say the box is on the ground.
Wait. Let me see. The ground gives the box normal force.
Yeah, exactly. The ground gives the box the normal force. And so if we say that the ground gives the box a normal force, and let's just make up a number, 300 newtons upward, what is the opposite to this normal force? What's the opposite force to this normal force?
The weight.
No. Now you're wrong. So you were right earlier with the gravity, but you kind of mixed it up on the second time around. So remember how to work out the opposite force? It's very easy, right? It's got to be same magnitude, has to be 300 newtons. It has to be 300 newtons down.
Yeah.
But what's acting on what?
Box is acting on ground.
Yeah. So the weight technically is always between, the gravitational body. So in that case, Earth. So, that 300 newtons is basically the box pushing down on the ground. And we would not necessarily call that the magnitude is from the weight, but basically, it's from the contact. It is essentially a contact force here, not the gravitational force, which is the definition of weight. All right. So is that clear?
Yes.
So this third law is actually not hard, but it is something that lots of students get very confused about. There is always, without exception, always a force that is same magnitude but opposite in direction. But as a result of that, it's not acting on the same thing. It's actually acting on a different thing. It's always acting on a different object. Just like how if you have multiple people, then when A gives to B, one gives, one gets, but this must always be the same amount. And that is Newton's third law.
Yes.